Good afternoon and a very warm welcome to the Black Hole. Today we are going to learn about Turing machines and the halting problem. क्या है Turing machine? It is one of the earliest mathematical models of computation, and today we are going to explore the foundations of computation theory and one of its greatest hallmarks, that is the halting problem. Today's session aims to introduce theoretical computer science to an enthusiastic audience with as few prerequisites as possible. We are very grateful to our speaker. मेरे दाएं जाने मौजूद हैं मोहम्मद हाशिर इस्माइल. He is a senior student of mathematics at Virtual University with a bachelor's in computer science from FAST-NUCES, that is the National University of Computer and Emerging Science. His interests include geometry and computational complexity. तो देखते हैं ट्यूरिंग मशीन्स क्या है और हाल्टिंग प्रॉब्लम क्या है. मुझे बिल्कुल आइडिया नहीं है, आप और हम इकट्ठे उसको सीखेंगे. प्लीज़ वेलकम हाशिर इस्माइल. थैंक यू.
All right, thank you very much, Nir Saab. All right, so to start off with, we have to ask ourselves the same questions that mathematicians found themselves asking back in the day. This was the early 20th century. What exactly do we mean by an algorithm? Now, up until this point, we had an intuitive notion of an algorithm, by which we mean processes. So, for instance, as school children, you might recall Euclid's algorithm for finding the highest common factor of a group of numbers. Similarly, you might have in mind how to multiply, how to add numbers. Now, the question then emerged, how do we formalize this idea? How do we formalize the act of performing these sorts of calculations or computations? So, during the early 20th century, renowned mathematician David Hilbert had essentially proposed his 23 problems. Now, relevant to us is essentially his 10th problem, which kick-started the development of computing as a field. All right. My apologies to whoever drew on the board and Mr. Turing over here. All right. So Hilbert's 10th problem essentially asks regarding Diophantine equations. So equations of this form, or more general, but where you're discussing integer solutions. More specifically, Hilbert had asked if you could solve series of Diophantine equations with the help of an arbitrary algorithm. And then more generally, Hilbert and Wilhelm Ackermann had asked if you could, by an algorithm or some formal process, prove whether any logical statement is universally true. Sounds like a large leap, but essentially solving Diophantine equations to a good extent can be mapped onto such a problem. So, by this point, I believe most of you may have heard of the name Kurt Gödel, most famous for his incompleteness theorems in the day. Although we can't necessarily discuss the specifics of that here, what's relevant is that Gödel's incompleteness theorems had essentially reached the eyes of Alan Turing in the 1930s, who had decided to represent Gödel's ideas, his results, in a more novel manner, which we now know today as Turing machines. This is essentially the first major event in the development of computer science, and rightfully so is the birthplace of the field as a whole. Your modern computer is dependent on the fact that Turing had published what he had at the appropriate time. So, let's actually get into the nitty-gritty then. So, first published in 1936 under the name A machines, but later renamed to Turing machines, we start by outlining a rough idea of what a computer is. So, how exactly would you describe a computer?
From a very, very layman principle, as I know up till now, okay, input, we have an input, and the computer performs a set of processes on it, yeah, like works on it, and it gives us an output. So that's a machine basically.
Okay, so interesting thing. What you've actually done is provide us with an informal description of an algorithm, not a computer. But you can sort of see now by the nature of the question that the two problems are closely intertwined. In fact, that's one of the main results we're going to actually see along the way. But intuitively, the idea of a computer as it stemmed back in the era was some sort of abstract machine that could do precisely what you're saying. It could read, it could determine, and it could act. The key idea was that the mindset of the era was mechanical. So I'll perhaps start off with a more abstract representation before actually getting onto the formal definition. Again, my apologies. All right. So Turing envisioned an abstract machine as follows. You have some sort of black box. We don't know the specifics of what's going on inside. Now, okay, I'll actually draw it a bit like this for reasons that will be explained shortly. Now, this black box is connected to some sort of tape. With this tape going on indefinitely. This tape is where this machine is the source of this machine's inputs. The tape is divided into discrete cells so that the machine is aware of what constitutes a single symbol. And the machine has the capacity to move about the tape left and right. In fact, I'll actually just perhaps give it a set of wheels just to elaborate the point. Now, some key things about this machine that make it special. One, it is deterministic. What we mean by that is that for a fixed choice of input, we always know how this machine will behave throughout its lifespan. And second, it is sequential. There's no element of probability, and we are fully aware of what's going on with this machine. That was essentially the mental picture Turing had in his mind. But what is not quite clear is how this mental picture relates to the more formal definition that he outlined back in 1936. So, now on to the actual meat of things. We define a Turing machine as follows. All right. So first thing we need is a known finite set of symbols that the machine can work with. Why do we insist on finiteness? Because essentially, there is no concrete way to determine how to act in the case of an infinite symbol list. So, this set we shall refer to as the alphabet. This consists of every possible symbol that the Turing machine may or may not be exposed to.
So if my alphabet set is just 2, A or B, or 0 or 1, is that good enough?
Yep, that's
So
sufficient.
There's no lower limit.
There is no lower limit. All you need is that sigma should be finite. All right. Now, one symbol that we may have to introduce, however, is the blank symbol, which we're going to force into sigma. This is a forceful append. This is a forceful addition. This is just meant to indicate that a spot is empty. Now, now we have another finite set which we denote by gamma, and we call the external alphabet. The only distinction between gamma and sigma is that sigma may contain additional symbols relevant to assist processing, like the blank symbol. But gamma consists of all of the ones that you would practically care about in terms of input. We have another finite set, which we denote Q, and this is what we shall refer to as the external alphabet. It's just a subset of sigma. Essentially, every alphabet excluding those we might need for the sake of our own processing. So for instance, if you have to introduce artificial symbols to manage things like separating inputs or accounting for a blank space at the end or denoting a limit to your tape, you would have to include those necessary things in sigma. Gamma just consists of all of the important symbols that you care about in your context, like as the professor had asked, 0 and 1. Those would end up being thrown into gamma.
Gamma is the internal alphabet or the external alphabet?
External alphabet, that's just what we refer to it
Why
as.
don't you write it down over there so that we remember?
All right. So, all clear so far? All right. Next, we're going to have to specify an initial state. And now, perhaps the most important component, actually capturing the act of computing or processing. We're going to define what we call a transition function. Is anyone in the audience unaware of set theory notation for functions? All right, but if there's any ambiguity, please feel free to ask. All right, so we denote this by delta. Now, we want the machine to be able to process on the basis of two things. One, what it has read, and two, its current state. So at that point, it should be clear that the domain happens to be But now the question is, what does the output look like? What does it actually do? So it should be clear then that this machine can now decide what new state to enter. And since we had stated earlier that we wanted our abstract black box machine to be able to write on the tape as well as read from it, then it must be the case that we also include sigma over here. Now, does anyone recall any other property we expected from the tape?
Don't you have to have an instruction set as well? The machine will process data and it will give you output as a result of that. So something that says, okay, add these two numbers together, or multiply them together, take the square root or whatever. So where's the instruction set?
All right, that's actually an incredibly strong question. So what you're describing turns out to be another model of computation. Yeah. Essentially, the instruction set in the case of the Turing machine is actually not necessary. You embed everything within your set of states. The idea of an instruction set type computer can be represented using an incredibly elongated Turing machine. The only notion required is actually the idea of having states. The instruction set is actually capturable here. We'll actually construct an example of a Turing machine as we go along. But yeah, what you've asked is you've essentially presented us with another model of computation which ends up being more practical than the Turing machine for the sake of designing algorithms, but in terms of power is equivalent, which is quite perplexing considering the apparent limitations over here. All right, we want our machine to be able to read the tape left and right. So we're just going to add a small snippet over here. All this indicates is where the machine is moving next. So based on its current state and what symbol it has read, it decides the new state, what symbol to write down where it once was, and where to move next. That's what the transition function does. The key power of the Turing machine lies in the state set and the transition function.
Where is it that we are putting in what a machine is supposed to do? The machine is, after all, not making is not generating its own problem.
Right.
We are giving it a problem. So where is that information?
Right.
In which part? Is it in the gamma?
Actually,
the external alphabet?
No, actually it's just the last thing I needed to mention, which is the configuration. That's precisely what you had actually needed. So
I meant more like the goal. What is the goal of a Turing machine?
okay, so
what does it say? After all, we can make an infinite number of different Turing machines, can't we?
absolutely. Okay, so the goal of a Turing machine, or its intrinsic notion of what problem to solve, independent of input, of course, that ends up being captured by the way you design your state sets and your transition function. Essentially, all of the technicalities of the Turing machines is embedded within these two concepts. Because the transition function is responsible for deciding how to act based on what it sees. The transition function is your only way of knowing what to do. And of course, based on your problem, you will have to decide beforehand how many states you're going to be working with. Does that help? All right. And then the last thing is that the Turing machine, throughout its lifespan, has a configuration. This represents the total context of the Turing machine and has three major components. An infinite sequence, sigma, consisting of symbols from capital sigma. This represents the total tape. Of course, at the end you could have arbitrary many blanks, but what matters is that the total tape has some representation in the context. A cell number, P, this just indicates the position on the tape that we've actually reached on the Turing machine. And then, of course, the current state Q. So, with that said, we now have a complete abstract definition of what a Turing machine is. Now, I'm sure this is the case. It's not quite clear yet how exactly is this powerful, or how does it compute at all. To me, it's not quite obvious how exactly is this able to capture the idea of an algorithm in the first place. But it is in fact one of the most powerful notions of a computer. So to start off with, we're going to consider a problem. All right, now it seems I'm going to actually require the second half as well. I'd like the definition fixed there just so that we can keep it in mind throughout the process. Oh, okay. Thank you. All right, so we're going to start with a fairly basic problem. Let's suppose we start with some binary number. What we mean by that is just a collection of ones and zeros. So for instance, this is an example of a binary number. In fact, this actually equals 17. So, the problem we're going to consider as an example of building a Turing machine from scratch is I want a binary number. That's what I'm going to start with, and I want to reverse it. I want to mirror it. So, for instance, what happens to this what happens to this if I flip it? Nothing. But what about, what does this become? Yep, 1011 over here. What does this become when I reverse it?
The number?
When I mirror it.
अभी तो ये है
Not the value, just the symbol.
It's 1101.
Right.
वही मैं कह रहा हूँ.
Right. So we want to build a Turing machine that can do the job for us. Given an arbitrary binary number, it'll mirror it. So we're going to start with an abstract discussion on it about what the machine should be doing, and then accordingly we'll try creating a state table for it. Okay, so to start off with, what comes to mind when you think of something that tries reversing this sort of number or this sort of string?
It's a mirror.
Right, it is a mirror, but a computer can't. A computer has to define that mirror in a very minute way. The mic.
So the thing that comes to my mind is the computer shall see that if the number has an even number of digits or an odd number of digits. First of all, it will do that, and then if it's odd, then the center number will be considered as the mirror axis, and then it will flip the numbers according to their order, just like layman way.
Oh, that's a good shot. The idea of how the number being odd or even will matter.
Let's we don't know what you have in mind.
Oh, all right. Okay, so we're not quite, all right. Before actually getting to defining the state table, we actually need a clear idea of what the working of the machine would look like. We need to be able to emulate the machine ourselves before we can outline it for us. So, So just given a sequence of binary digits, here's the idea. When we start off, when our algorithm starts, we're here, we're at the first digit. Now, right off the bat, we know that this is always going to swap out with the last digit, the first digit is going to swap out with the second digit, and so on. Or in other words, that's essentially what's always going to happen. Now, the only problem of interest is what happens when n happens to be odd. Now, of course, we are aware of what to do in the case of n being odd. For us, we can just immediately notice that it's a central number, like in this case. We've spotted that it's a number in the center. The problem is actually getting a computer to understand that that is a number in the center. So, any ideas how we would actually get the machine to be aware whether it's dealing with the number in the center?
Count the number of digits.
Right. Or in fact, perhaps simpler than that, we could just start off in some state that knows it's even. Because having no symbol is the equivalent of having an even length symbol in a string in the first place. Right? So we start off on the assumption that we're in even, and as we encounter symbols, we start realizing that we're actually odd. All right, I'm here. I'm aware that I'm over here, and right now before I start reading this input, I think I'm even. I see this symbol. I realize now that I have an odd number because so far I've only seen one symbol. Now I move right.
Now again
Even.
Okay.
Odd. Even. Odd. Even. Now when I see nothing to my right, because the right can be blank, is unboundedly blank. When I realize there's nothing to my right, then the most recent conception I had about my length, whether it was even or odd, is going to be critical in deciding whether I have to worry about the central number or not, the central digit or not. So, how we deal with this, of course, this is a naive idea. We could deal with this in an arbitrarily. We separate the case into two, based on whether there is a central number or there isn't. Now, if there isn't a central number, then here's how the machine would work. Start here. Mark it. Remember, gamma is what we're using to specify the input. But for the sake of processing, we can do whatever we want. We could add a tick mark, we could add an underline, we could highlight a number. Essentially anything that could assist us in processing, we can specify. So I'm just going to mark this. Now, what am I going to do when I've marked it? I'm going to keep going right until I've realized there's nothing there. Once I've realized there's nothing there, I'm going to go to the left and I'm going to do the following. I'm going to exchange it with a 1, and I will remember the fact that I had just erased a 0. I have to keep that in my mind throughout the process. Then I will go left until I encounter the number I had just marked. And swap it out with a 0. But there is a technical problem with what I've just described. Any ideas? Any guesses? So once I've jotted down a 1 and a 0, now there is no way for me to tell whether I've already dealt with these symbols or not. There's no way for me to know. How can I indicate whether I've already processed these? I don't want to process it here again, otherwise I'm just going to remain in a loop of sorts. So, a correction to what I had stated earlier, when I make these replacements, I'm going to add a mark above. This serves no purpose other than to allow the machine to remain aware of the fact that it has already made that computation, or it has already made that swap. That is all it does. So we've made the swap. Now, we're back here. I go right. I realize I need to swap this. Underline. Keep going right. Now, the distinction here is that any symbol that has a bar, or a line above, I view that as the same as reaching emptiness. So I get here, I realize I'm done, I've hit my bound, I go left. Now since I knew that I had just written a 0 underline, I swap it out with a 0. And I'm now forced to remember that the symbol I had just written was a 0. So now I go left again, except this time, when I see an underline number I have to swap with. And I can put a bar above. Does that make sense?
Yeah, but where is the information stored that you've put a bar? In which one of these sets?
Sigma. Again, gamma will consist of all of the symbols that we are concerned with as a user or as someone describing a problem in abstract. But sigma is where we will permit ourselves some working space. Sigma, besides the necessary symbols, allows us to basically represent scratch work.
Okay, where are the delimiters? So you can't go too much more than the last one to the right?
Actually, here's the thing. You can go arbitrarily to the right. To the right, there's no bound. The tape is infinite.
But then you couldn't do this computation because if there are an infinite number of symbols, then you can't reverse them. That would take an infinite amount of time.
An infinite number of binary digits appearing. Right. In the case,
you have to put a delimiter.
Right. So the blank symbol, which we had introduced over here, I'm not writing it for, you know what, I'll actually mention it here as well. There's an arbitrary number of these trailing on the right. That serves as our delimiter for the most part. By nature, we have constrained ourselves to dealing with inputs that are finite. The Turing machine itself is a finite object, as you can see by the definition so far. The only purpose of the blanks is to permit ourselves arbitrary working room towards the right. However, one condition that I should have mentioned.
But even to the left.
Oh, right.
You need a delimiter on both sides. Otherwise, you won't know that there are 6 symbols.
Good catch. That's actually the thing that I'd missed. So towards the left, we have to specify one important constraint on the machine. Good observation. Okay. So P here represents our current position. It's a natural number. I'm going to count 0 for the sake of it. We're going to specify one thing on the configuration, which is that P must always be greater than equal to 0 throughout the execution of the program. The moment it hits a negative, you crash, the machine should immediately crash. This ensures safety on the left, as you had managed to point out. So if we design a bad machine which doesn't recognize when to stop on the right, then we're stuck. We're not going to finish. We're never going to finish in finite time. But by ensuring this, we at least know that there is a bound on the left. So going forward, it is only a matter of our competence and not necessarily a point of genuine concern regarding the tape itself or the nature of the tape. And does that clear it? All right. So again, at this point, it should be clear. Underline this. Move to the right until you see a bar. Go left. Swap out. Go left until you see an underline, and then notice a bar. Now, all right. No more bar, there are no more digits without a bar. Everything has a bar. I've essentially done the processing. So here's what I'm going to do just to clean things up, because this tape is now going to represent the output. I'll go back to the left, to the extreme left. And I will essentially start removing all these bars, going one by one towards the right until I hit the end. So that covers the case for an even number of symbols. The problem stems when we try applying this to, say, an odd number of symbols. So, why doesn't this really, so based on what we've done here, any ideas whether it should work out here or not?
So I guess this will repeat just as for the even numbers, it will repeat. But as we go, reach the center number, we'll reach a dead end. So we'll stop there. Is it?
Once we've reached the central number, we've realized we have a normal digit, but to its right, we have a barred symbol. So on the one hand, remember, when you're dealing with this machine, you are not aware of the whole context. This is because of the fact that this set of states itself is finite. You can't remember everything about the whole situation. So to the lay machine, this could either be something that has something to swap with, or it could be the central number. We don't know yet. So this is a predicament of sorts. Any proposals on how we would deal with the central number?
The machine will look both to the left and to the right of this number, and if both of them have a bar above, then this means that it is a central number.
All right, good. So that would be one. Yep. So that's essentially one solution to dealing with it. We look left and right whenever we see a normal integer, and we check whether both sides are barred or not. So that would essentially deal with the issue at hand. So we cover the even cases and then we cover the odd cases. So shall we construct the actual machine itself? All right. First, I'm going to start off with outlining sigma. I've already inserted the blank symbol here. All right. Now we've outlined these two. Just keep these in mind because unfortunately we're going to have to erase them shortly. Reason for that, defining the set of states and the transition function itself, chunk of that board. Implicitly, I'm going to define Q using the transition function. So anything that you see in the leftmost column, consider that an element of Q. All right. Oh, by the way, so one thing to mention is that Shariar's suggestion for checking left and right of a normal integer, that essentially overcomes the need for actually checking whether the length of the string is even or odd in the first place. Because if it's even, you will in the case of it being even, you'll notice that one digit to the right ends up not being dealt with. All right, so we start off, we see a 0, and then what shall we do? You know what, I'll just denote this by Q just for the sake of notation.
What is the second column?
Symbol, the one it's currently reading.
Symbol.
All right. So we start off in this state. I'm going to denote it with an arrow here. It sees a 0, and then unit to the right. Same state, if it saw a 1 instead, it would go into Q1, drop a 1 with an underline, and then go plus 1 unit to the right. All right, so for the sake of brevity, I might try mentioning multiple cases at once in this over here. All right, so far in this state, it only cares about the conclusion, the ending. So if it sees a 0 or a 1, which is an intermediate symbol, it's just going to ignore it. And go 1 unit to the right. When it has reached the end of the right, so this could be either in the form of a blank symbol or a barred symbol, as we had discussed earlier. It's going to reach the right, and then it realizes it's done with its working space. It's traversed the entire working space. So we'll now introduce another state. which we call Q naught prime. It's going to reach the end, realizes it's hit the limit, and then it's going to go left. And now it will know that whatever is on the left, it will have to replace. So, now because it only gets to Q node and hence Q prime node when it initially sees a 0, it will always be aware that no matter what it sees at the right end, that is a permissible to edit symbol, it will always swap it out with a 0. Is that clear? Make sense so far? Okay. It's just a more abstract way of writing what we had been doing. We start off here and we check whether we have a 0 or a 1. If we see a 0 or a 1, we underline it and then we start going right. Now, these states assume that you saw a 0 first. That's an implicit assumption. That's why I named it this way. You saw a 0 first. Now, if you see anything on your way to the right, ignore it, because you want to know where the limit is first. Once you hit that limit, that now is the time you can actually start writing. Indicated a separate state. This indicates write permission. So, once you have the capability to write, whatever symbol you see, because this sequence of states assumed you saw a 0 first, you immediately know you're dealing with, you just have to write a 0, either case. You see a 0, you plop a 0. See a 1, you plant a 1. I may have to name this something else. All right. But now here's a problem. I haven't described a way for us to actually remember whether we replaced a 0 or a 1. So I'm going to actually specify not 1, but 2 states at this point. If you saw a 0, you'll go from Q naught prime into Q naught naught. Otherwise, you'll go from Q naught prime to Q01. This just indicates what you've written up to so far, or what your pair was, so to speak.
Put a double bar.
Right? We could honestly specify either. There's actually multiple ways to realize a Turing machine for the same problem, as you'll come to realize in the construction. Similarly, for the case of 1, we'll be doing the same thing. At this point, it should be clear what we would be doing in the 1 case either. All right. The non-trivial states to define would be these. So we'll start with Q naught naught. Nothing on the left. Nothing. Just now, when it sees an underline symbol, as before, with 0 bar, at this point, it should be able to deal with it. It already knows it started with a 0. It sees the underlying symbol, which means this is the one I was dealing with earlier. Replace it with the 0. Go 1 unit to the right and enter this new state that I've yet to define, which I call QS. QS is going to be implementing precisely what Shahryar was suggesting. Likewise, if I had Q01 instead, and it saw the 0 bar, enter QS, swap with a 1 bar, and go 1 unit to the right. Now, does anyone have any ideas or guesses as to what would happen if it saw a 1 underlined at this point in time? Based on what we've written so far. If you picture yourself being the machine, what would happen if you came across this, knowing that you were here or here?
Going to replace it. But anyway, how long is this definition of the Turing machine going to take?
As you can see, it's going to take us perhaps the entire span of the chalkboard if we keep going about it. So for the most part, I'm just defining what are the non-trivial states, and then from the rest we could extrapolate. As you can see, this is why the Turing machine, although a good theoretical model, is not necessarily the model we use for practical purposes when we're discussing algorithms. It's quite evident, isn't it? We have a basic problem. We just want to flip digits. But already we've had to construct how many states? We've already had to construct 7 states, excluding the states that we would have to build if we saw 1 first. And we have yet to note the states to incorporate what Shahryar suggested regarding checking left and right. But regarding the question in hand, if we follow the sequence, this table as it is, we realize if we see a 1 underlined and we happen to be in either of these states, we have hit a contradiction. We could not have started with a 1 underline if we were at this state, at either of these states. Because the only way for you to write a 1 underline would have been if you were in the Q1 state to begin with, and then you would have been in Q1 prime or Q10 or Q11. You would not be. Clear? So are we good so far? We've done everything suggested. Now all we have to do is incorporate his sanity checks. So it doesn't really matter what we see at the position, because this is what we're assuming is a potential central number or a potential left number. We leave it as it is, we go left. And now we note, again, well, the notation is going to get weird, but I'm just going to define a state which is just, forgive me if it seems like I'm trying to define a time derivative. +1. And now I'm forced to take up some space over here, just so that we keep the flow of things going on. Actually, wait, right, I could have just defined this as QSR. QSR. I see. No, I actually started off with a regular number.
Middle one.
Huh. So I could not see a bar or an underline yet. That would be contradictory. Leave it as it is. This dot just indicates we've gone one position. It's nothing mathematical.
0, 1,
Plus 1. And if we happen to be in QSR accented with a dot. Now, this is where things matter. If we see a 0 or a 1, then that means right now we're dealing with something that has a number on the right. So it's not done yet. So we go left, leave it as it is, and we start back on this state because now we can start all our computations again because we know there's something to deal with on the right. But if we had seen nothing on the right at this point, this is the case where we realize we've actually hit a central number. Not quite, we won't terminate yet. Again, I'll have to define another state. Again, at this point, it should be clear this is arduous. Leave it as it is. And then I go 1 unit to the left. All right. Now, although I've specified over here that the cell number should be greater than or equal to 0, at this point it should be clear just because of the safety checks. If I hit the last digit and then I go left to check it, or if I'm trying to go left, I don't know how to decide whether I'm at the end or not without immediately crashing. If I started off in the middle of a binary number, and so on, and I'm going here, left digit by digit, I'm going to say that I don't know what's on the here. If I go left and there is absolutely nothing on the left, my machine crashes.
But there is a delimiter there. You already put it in, so how your machine has to stop there. It encounters a delimiter.
Right, I'm actually getting to the caveat of your point, which is there's a delimiter over here. Earlier, I'd only stated that p should be greater than 0, equal to 0, otherwise it would crash. So implicitly, we shall. The problem is we essentially still want it to crash on the off chance that we're constantly trailing to the left. Right.
The first digit rather, so in this case what you have over here is a 0.
Right.
You cannot go left if there's a delimiter there.
Right, exactly. The problem is, however, that we need the machine to know that there's a delimiter there. Otherwise, as stated before, if we only impose the condition that p is greater than or equal to 0, you can't capture that as a symbol.
No, but wait, if there's a tape and the tape has got zeros and ones on it, and then there's a portion of the tape
That's a blank. That's a blank symbol.
A blank
is written on, but we can't write on the delimiter. Blank spaces.
Blank spaces we can write on, but we don't want to. We want to protect that delimiter you're suggesting.
So we can use a new symbol like X.
Right. Again, this is where the convention for machines seems to differ greatly. Again, we're debating on it right away as we speak. Kitaev defines it a different way. Christos Papadimitriou at this point would introduce another symbol and then force that every input symbol starts off at the 1 position, not the 0 position. That's one way to deal with the issue. But yeah, there's multiple ways to deal with the issue you're describing of the issue of the left delimiter and the right delimiter. I'm making the point here so that we're aware that during our naive algorithm, we still have to make some corrections to and whatnot. It's not a complete picture yet. But we've made the safety check. Now this state, Q sub capital L, this is just going to keep going to the left. The only symbol that it should care about is that left delimiter I've just defined. And now at this point, I'm going to leave the other input states it leaves to your imagination, but for the most part, it's just not going to do anything if it sees anything else. It's just going to leave it as is. It's just going to hit that left delimiter we wanted.
So can't we make it terminate?
Okay, we want the tape to capture our input and output. Where the input and output are on the same tape. When the machine is done, we want to be able to look at that tape and physically see what it spat out. Now here's the problem. You and I might not care about the bars, but when the problem is getting incredibly complicated, we want to confine our output. We want to make sure the output is same as intended. So at this point, we hit the bar state. We see a 0 bar or a 1 bar. And we convert it to a 0 or a 1. Go 1 on the right. And then, when we hit a blank, we need to terminate, right? So at this point, you'll notice, where am I going to specify a termination? I haven't specified a place to terminate. So, there are 3 major states that are always considered a part of your initial set of states. These are additional. We have to augment them into Q. These are the yes state, the no state, and the halt state. We forcefully inject these into Q. The point of this is to hit precisely what he suggested, which is we want to stop. And so are we all clear so far in terms of how it works?
So this is also in ASCII in yes, no, halt.
No, I've just written it that way. We could denote it in any way we want. I'm only writing it this way just so we're
But
clear.
ultimately, it has to have a binary representation because you have only zeros and ones.
Oh no, that's just the name of the state. It's not a symbol. States are internally named whatever we want. Regarding the representability of the states, we're actually going to get to that right after, regarding naming and whatnot, or as you said, the ASCII convention, or binary representations. For the time being, we're just using this as a name, a self-describing name.
Okay. Okay.
So, are we clear on the processing of the table for most of the cases? So,
Okay, so your head keeps going back and forth until it's
done, yes. And it is a marvelous result that this is perhaps the most powerful sequential deterministic computation machine of sorts. Everything else is equivalent to it. Now, any issues that you've noticed so far with the way we're approaching computing so far, or the way we're describing algorithms? Could be anything. You have a question? Oh, okay. We have to define an extravagant number of states just to perform the most basic processes. That's one problem, which is why in the study of algorithms, we don't often use the Turing machine model at all. We just use an equivalent model. That's why your computers use instruction sets to avoid this. That's why you need instruction sets. And then in addition, there's the other issue he's described, which is I could have a different symbol set. He could have a different symbol set. How do we deal with the issue of cross compatibility between machines if we wanted? So it should not be the case that he has constructed a binary digit reverser and I've constructed a binary digit reverser, but when we give each other our input tapes, then they should result in different outputs, or they should behave in ways that do not reflect the output on the output tape. And in addition, there's the fact that so far a Turing machine is specific purpose. What if we want something general purpose? Your computers are general purpose. They can do whatever you want. They could run PowerPoint, they could run a LaTeX code, they could run a browser, they could play a video game. They're general purpose. There is no hint of general purposeness over here so far.
You need a stored program.
You've actually gotten to another computing model already. Are you sure you haven't studied computer science before?
No, I haven't. But it's obvious. It's obvious that you need that.
And it was obvious to one.
Because of what you're telling us, that it needs to be able to run this, that, and
exactly
different applications.
And that's precisely why von Neumann was the father of the stored program, the idea of the stored program. So, pretty much, common sense is the key factor here. So, we're going to introduce something new, and this is where the magic of Turing's work happens, and this is also where computer science actually starts expanding or building out. This is also going to be the thing that actually inspired von Neumann when he was working on the ENIAC at the Institute of Advanced Studies, which is, I believe, right next to Princeton in New Jersey, if I'm not wrong. Okay, now at this point, no one has any objections if I don't actually write down states or transition functions, right?
Yes, absolutely not.
Right, at this point it should be trivial. Okay, here's what we're going to do. We're going to define what we call a universal alphabet. In this, it could be the binary numbers, it could be the ternary numbers, what matters is we now fix some sort of universal symbol set. We'll call it sigma bar. And now, here's what we're going to do. We're going to define what we call an encoding function. So, at this point, I can encompass all of this, the notion of a Turing machine, as just some finite object M. No objections. Finite object, the state table, no matter how long, is itself a finite concept. Likewise, any alphabet that the machine describes as finite, all of the symbols we deal with are finite, the states we deal with are finite, the transition function is finite. So we can describe the entire Turing machine as a finite combination of some universal alphabet. Or in other words, we can encode our Turing machine in some alphabet of our choosing. So in your case, so as you had stated earlier, it would be the binary numbers or the ASCII symbols. We have now permitted ourselves to encode a machine.
This is like Gödel numbering, right?
Quite, yep. Same idea. That's why Turing's paper is explicitly titled "On the Computable Numbers in the Entscheidungs Problem," and he explicitly has to cite Gödel. There's a reason for that. Same principle. In fact, we'll get to the end, towards the end, we'll realize that he's essentially restating Gödel in some weaker way. So we can encode machines. Now, we define what we would like to call a universal Turing machine. Now, how would it work? What are we going to do? Well, first thing to keep in mind is that every Turing machine, throughout its process, if you ignore the intermediate steps, if you only concern yourself with start and end, it computes what we call a partial function. It could be used to evaluate some function from gamma star to gamma star, and this just denotes the output on the tape. Functions of these categories, if a function of this sort, by the way, quick note, when I say partial function, I mean it is not necessarily defined for every input or every element of the domain. Now, if such a function, now the reason I call it phi sub m is because this is the minimal or natural function that is evaluated by the corresponding Turing machine M. This is just the one we get by definition, if we only consider starts and ends. And that's the reason why I mentioned the output situation, because we want to restrict the output on the tape to gamma, not sigma. We don't want the user to care about the processing beyond the blanks. Now, we say that a partial function f is computable if there exists a Turing machine, denoted M, such that phi of M, phi sub M is equal to F. A function is a partial function from sigma star to sigma star. And what I mean by sigma star is just the set of all strings you could construct using gamma. So when we were dealing with 0 and 1, this consists of all of the binary numbers. Such a function is computable if there exists a Turing machine that yields the same results all the time.
What is this f?
Oh, this is just a dummy function.
Oh, f is what takes gamma star to gamma star.
Right. It's a function, but we don't know if it has a corresponding Turing machine yet or not. Hence, we said the function is this function is computable if it is the function of a Turing machine. Of course, the Turing machine defines one function on its own, but then in general, we don't know if a function has a corresponding Turing machine or not. Hence the explicit definition. Now, we define the universal Turing machine as follows. It corresponds to some computable function that takes as input two things. The only reason I'm using capital U over here and little u over here is to indicate the separation between machine representation and function representation. But the idea is it should take the encoding of M, the representation of M, along with the input that M was supposed to compute on, and then emulate M. This is sufficient in describing a universal Turing machine.
Any Turing machine.
any Turing machine M, provided you've already encoded it in your in your universal alphabet. Give it a description, give it an input, it should deal with it. Is this clear? It seems as if we've just handed this upon high.
Where does X belong to?
Good catch. X happens to be something that we have, right? We have to deal with the issue of actually representing X itself. So we're just going to pop in encoding here as well. We've now encoded X within
the domain of X.
Oh, the domain of X. The start of this. The set of all strings from here. X itself starts off in the domain defined here. This M defines some gamma. But the problem is, it defines a gamma and a sigma. But the problem is, we want to make a general purpose machine. So the idea is, when we encode M as a finite object, a series of binary numbers, for instance, in this alphabet, then it should be able to use the representing table to know what do I have to do to this. So for instance, X started off, for instance, as say an English alphabet, but then we turned it into a binary number. When this function looks at M in its binary representation, it should be able to read it and realize that, oh, this is actually an English alphabet, say A. So for instance, if I was starting with the integers from 0 to 10, and I had X is equal to 5, then when I convert it into binary, which ends up being when I convert it into binary, the machine will not know will not know immediately that this is actually a 5. It will use this, it will use the encoding of the machine we want to emulate to figure out what is this. So is this construction clear so far? If there are any questions at this point, please ask, because this is perhaps the most complicated construction despite the apparent simplicity. Are we clear? All right. So this is what we call a universal Turing machine. Any machine of this form. And this is where von Neumann actually got the idea of the stored program. Turing actually gets to this point towards the end of his original paper, and at this point von Neumann realizes that instead of targeting a specific purpose computer, he should consider some sort of representation of programs that he can store on memory. Implicitly, this is where the motivation for the ENIAC and the von Neumann architecture came from. All right. Now we're going to get to the actual problem at hand. So what interesting questions could you have regarding a general Turing machine if you caught one in the wild? What possible thing could you want to ask of it?
The infinite number of questions you could ask.
Right. There's an infinite number of questions you could ask.
How do you factor a number?
Right.
That's too complicated. So many other. There's no limit to such things.
Right. There's no limit to the questions we can ask. But one question that had caught the eye of Turing because of the work of Gödel, which was does there exist a Turing machine? Call it H. That can tell if some arbitrary Turing machine M Does there exist some general Turing machine that can tell if another is going to perform its computations in a finite amount of time? When I say halts over here, I mean either yield a yes, no, or just stop immediately without declaring yes or no. The only distinction between these is the indication to the person, to the observer. So, any guesses?
Yeah, but there is a difference. It could stop because it solved the problem,
Right.
or it stopped because it realizes that there's no solution to it.
Right. Either case. But the main problem at hand, because when in the initial history of computing, the main driving force behind the idea of an algorithm was the hope of it being finite. So you're right. There's a different semantic quality to it, but syntactically, it just indicates that the machine stopped in finite time. We don't want it clacking away forever. So, any vague guesses to this problem? Yep, that's the whole point of the session. That there exists no such machine. And we'll construct a partially rigorous proof. I say partially because there's a slight caveat I'll be ignoring. So, to start with, we already know at hand that we don't suspect a machine can do this. Any ideas as to how we would prove it?
A counterexample, perhaps.
A counterexample in some way, yes. But we need a clearer argument. How are we going to deal with the issue?
Because if a function doesn't halt, then it will take an infinite amount of time to tell whether it actually doesn't halt, right? So if there is a function that does halt, then the machine will keep chugging away at that whatever that is.
Here's the thing.
Yeah.
This question we were asking, the machine is not required to emulate what it was fed. It only needs to look. It's the same as asking, if I see someone else's program, can I tell whether it will terminate in a finite number of executions?
But wouldn't that machine have to carry out the computations all
Not
the
at
way
all.
all the way through
Not
to
at all.
determine
Potentially
whether
not.
it halts or not?
Potentially not.
So if a machine doesn't halt, then for example, if it takes, for example, a billion steps before it halts, and there is a machine that doesn't halt at all, so your machine that checks whether which of the machine is halting, it will have to check for all of those steps, right? How can it tell before having checked all of those steps whether one of the machine is halting and the other isn't?
But
Right.
one way is that if you can see that there's a loop in the program, then you can immediately say that it's never going to stop. So you just put a loop and
Right.
it's easy to do that.
Right. He's already getting to the point where we don't have to execute it itself. We could just observe the structure.
Yeah.
We could look at the structure of the machine. But you're also right in suggesting that it seems unintuitive that
For example, the digits of pi, for example, irrational numbers, they keep going on and on. We don't know whether they repeat after trillions of digits or whether they're actually not repeating. So that's what I'm saying. So there must be cases, there must be Turing machines that will require you to check all of those steps, infinite number of steps, to determine whether it actually halts or not. So that's why it's impossible to, in general, to determine for any machine whether it is a halting.
not quite. You're on the right idea, but not quite the way to get to the idea. This is where we sort of have to introduce the magic of contradiction. This is where you cannot have a constructivist proof of the situation. We have to escape constructivism. We cannot do this in that sort of manner. All right. So we're going to prove the point that there is no such Turing machine that can determine whether an arbitrary machine halts or not. So, since these are all finite objects and they're all countable, this is the key trick, they're all countable. I'm going to define a table here. This is the I column, this is the J column, this is the J row. All right. The reason I'm using I and J, which seem like similar indices, is the fact that once we've denoted a binary representation for both machine and input, then it doesn't matter. They're both numbers at the end of the day for our purposes. No objections? All right. So I'm just going to so this denotes the ith Turing machine, and this denotes its output for the jth number in n. We're dealing with the naturals. So for instance, this could be 1, this could be 0, 0, and so on. Likewise, this could be 1, this could be 0, 0, 0, 1, 1. Unbounded here, unbounded here, unbounded here. Because we're talking about n. We're basically just talking about n cross n at the end of the day. Now, here's the trick. If H existed, then essentially we have this kind of table, right? If H existed in the first place. Then basically you're saying you have this sort of table. Now, construct G as follows.
Can you repeat what H means?
Oh, it's just what we're calling the halting machine. The hypothetical machine that checks if another halts on an input. It's a dummy machine. H is just a dummy name.
Yeah, but what is I and J? Repeat again.
Okay. When we were talking about universal machines, we said that they take a machine and the input in the form of an encoding. But since every finite encoding, finite in the sense of a single instance, not necessarily the whole set, since every finite encoding can be mapped onto the natural numbers because they're countable, I've basically just enumerated them in this way. So for instance, the binary representations of programs, at the end of the day, they're numbers. Long numbers, but they're numbers. That's the basic gist. We just denote them by the integers instead. We're getting to the meat of it directly without dealing with the representation of it. Is that clear?
The I's are the Turing machines and J's are the inputs.
Potential inputs, yeah.
Are the inputs that they take.
Turing machine number 1, 2, 3, is that what you want?
Yep. Turing machine 0, 1, 2, 3, input 0, 1, 2, 3.
Okay.
This is an index. This is not an actual value. Because once we've decided to encode machines, say as binary numbers, then implicitly we've already forced the Turing machine into the set of naturals, haven't we? If I say that there is a binary number that represents m, or if there's a combination of binary elements that represent m, then it's just a matter of me being able to interpret the number correctly. But the number exists. Likewise for this. So we've already made them enumerable, countably so. So we've built this, now we've defined this function. It's a valid function. It just looks at H and then does what it does. Now, so far everything's clear. This is a potential definition of the halting machine, or the idea of the halting machine. And we just built this out of nothing. We just built it using that. We have done nothing additional yet. Now, the main question.
So G is defined on X. What do you mean by G defined on?
X is still a natural number at the end of the day. We're not working with the reals. And by G of encoded G, I mean that G is now permitted to read its own representation.
Okay.
So, here's the problem. Here's what we've essentially done. What G does is this. It looks at this diagonal. So it sees a 1 here, it gives us a 0. It sees a 0 here, gives us a 1. Gives us a 1 here, it gives us a 0. Now at some point, at some unknown point, we have hit a position at which we can place neither 0 nor 1 without hitting a contradiction. For if,
How do you know there's a contradiction?
right, we'll get to it. If at this position we had say a 0, which meant it didn't halt, that essentially means H said that G will never halt on itself. But by definition, when G notices that on its input H says it doesn't halt, it immediately does the opposite.
Okay.
Similarly, if GG over here was a 1, it would see that and it would yield a 0. Or, in fact, no, I'll actually replace this since 0 and 1 are misleading here. If it notices that it halts, just loop. I'll ignore the 0s and 1s now, since that was technically incorrect. It loops, it leaves an undefined result. Whatever the case, it contradicts H deliberately. And because this is a valid function, H has to know it. H has to know it at some point because of the correspondence with the natural numbers. But if it does know it, you can force it to contradict itself. Hence, there could never be such an H in the first place.
Counterexample.
This is Cantor's diagonal argument. It's the same reason why you can.
Russell's paradox.
This is it's similar in spirit to Russell's paradox, and it's similar in spirit to Gödel. In fact, the halting problem can be used to attain a weaker form of his first incompleteness theorem. Though that's beyond the scope here. But yeah, when you're forcing this object to ask a major question about itself, it spits out a contradiction. This is the crux of the halting problem. There is no such universal machine in the first place. Reductio ad absurdum.
Is it as simple as that?
Yep. I mean, if you're a mathematical logician, you might iron out the details, like for instance, avoiding self-referentiality. But at the end of the day, the premise of the proof is the same. You take a table and then you deliberately contradict the diagonals. You can actually use the same reasoning to prove that the real numbers are uncountably infinite. If you've taken a course on if you've ever seen real analysis, it's the same body or it's the same proof. These are what are called diagonal arguments. And in fact, a more interesting result, in fact, a generalization of this. There's a theorem in theoretical computer science which is referred to as Rice's theorem, which essentially states the following. Any semantic question that you can ask regarding a Turing machine is undecidable. By undecidable, we mean there is no Turing machine that can spit out a yes or a no when it tries solving that problem. So halting is undecidable, and effectively any semantic quality regarding a Turing machine is undecidable. So you could not ask a Turing machine if it actually factorizes correctly. You could ask it a syntactic question, like for instance, does it have a loop? Does it break? but you cannot ask for correctness.
No, why not? If it breaks rules, then it has done something false.
Right, but you cannot tell that outside of it. You cannot tell that by observation alone. Otherwise, we end up at an instance of the halting problem again. Rice's theorem is a more powerful generalization which requires a certain more steps in mathematical logic beyond what we can state. But the idea goes that you'll enter a contradiction again of sorts. So there's no way for you to determine that a program is completely correct merely by observation. Or there is no general purpose method for it. There are specific methods for it, but there's no general purpose algorithm that can get the job done. So for instance, if we were talking about something that multiplied correctly, sure, we could use theorems from group theory to figure out whether it's working or not. But that process cannot operate on an arbitrary algorithm. We can't use group theory to figure out a general problem, like for instance, whether my browser is going to load YouTube or not. That's the essential gist. There's no general purpose approach. All right. So that's essentially the halting problem.
Okay.
So we can construct specific halting functions, but not a general halting function, right?
Yep, in fact, one machine that doesn't cause problems, you could just build a machine that checks if a Turing machine halts within n steps. That's perfectly fine. You could do that, but you can't do something of this sort.
Basically, you can generalize it. You can specify it.
You can't generalize, and you can't generalize in a way that it is universal, or that it doesn't have to care about the executions. So you're actually forced to weaken yourself by actually executing it up to a finite time.
So one example that came right into my mind when you said it can't validate a solution. Let's say if you factorized some number which has a certain prime factorization, let's say. So it cannot validate your solution, the solution it has done for you.
No, a general purpose algorithm cannot do that. If I write an algorithm that deliberately analyzes it for some sort of mathematical inconsistency that I'm aware of, that might work. But the same algorithm will not work if I talk about addition. Does that make sense? You would have to create a specific purpose algorithm to achieve that point. Now we've talked about computability, we've talked about undecidability, the fact that these problems can't be dealt with in terms of yes and no problems. But really the next step after computability is efficiency or effectiveness. I mean, it doesn't matter to me if my factorization, tell me this, if we propose two factorization algorithms, one of which would always would work out within say 10 steps and one of which would always work out in 1 billion steps. No sane individual would choose the latter over the former. So now we introduce a bit of complexity as follows. I'm just going to denote n now just to stick to the fact that we're dealing with naturals. And forgive me for the abuse of notation, but computer scientists have done this. I have no clue why. We say that f is in the O of g, big O of g, if f is bounded above by c times g for every n exceeding n naught. So essentially it's asymptotic growth. F is asymptotically bounded by g. Make sense? All right. Now we say that f
O as order of, what's it being used over here as?
It's the same. It is order of notation. It's just expressed in a different way. In fact, this is actually just a weaker form of Landau's little o notation. It's the same, but expressed in a manner more appropriate to discrete algorithms. All right. And we say that the Turing machine runs in T of n. We're just using T of n to denote the number of steps that the Turing machine had to run on. This is a time based relative to the input size. N now denotes the size of the input over here.
No, but how can that make sense? Because there can be many different Turing machines.
Good catch. Good catch. So here's the idea. There's two approaches here. There's two more approaches here as well. We could either force an index that mentions the specific machine, or we could choose the minimal of all machines. But right, for the sake of the discussion, I'll actually just add the subscript. So right, now this
For a specific machine.
for a specific machine for an input of size n. This represents the time it takes, the number of steps, not actual time. Now we say that f is in the poly of n if there exists a Turing machine M such that and F belongs in the poly of n if there exists some Turing machine,
Belongs in the
Poly क्या है? Poly?
polynomial of n.
you've written, okay, that looks like
degree n?
P dy.
Oh, sorry.
It's poly.
Right.
Yes.
Sorry for the spacing.
So polynomial of order n.
It's polynomial in n, not the order, it's polynomial in n if there exists some Turing machine that computes f, and that Turing machine's evaluation time, the time it takes, is on the order of some polynomial.
So it increases rapidly.
It's bounded above by a polynomial that could increase rapidly.
Above, yeah. Into the k.
Right. So for instance,
For k positive bigger than.
right.
Yeah.
So for instance, a naive algorithm for sorting, which is you start doing pairwise sorts. You have a list over here, you don't know, they're not necessarily ordered. So your strategy is you start pairwise sorting, and then you keep doing this for about until you've done n square iterations. So that happens to be bounded, so that such a machine, such an algorithm is in the O of n squared. This is what we mean by a polynomial time function.
This pairing thing reminds me of that, elementary thing in combinatorics, n choose 2 if I'm not wrong. Does that something to do with this? You said n square.
Oh, n square would be the running time. If I try sorting an entire list by pair by pair swapping, because if I tried swapping from the starting end all the way to the end, then by one run, I only know that the leftmost element, my right, ended up getting all the way here. That this item, or basically at one execution, I only know that whatever it does is at the rightmost end is the largest number. Second largest number might be incorrect. So I have to keep on repeating the iteration.
So that aligns with the definition. If we have two blank spaces and the n choices, and both of them have n possibilities, so n into n, which gives n square, right?
Not quite, because not quite, because if you
exponentials.
right, if you try using that sort of construction because what you're talking about is actually a state space. You're not talking about the algorithm. You're talking about the state space. State space would be potentially exponential. In fact, has to be exponential in terms of the number of
Here we have to
objects.
run n operations for all n elements, so that's why we are getting n square complexity over here.
Right. Now,
It's late.
oh right, right. There's no quote. All right. So I'll just state it informally here just to conclude things. The set of all algorithms or the set of all problems that can be dealt with by a function that's in poly of n, we denote that by p. Now, if there is here's what we'll do. We'll say that f belongs to something like non-poly of n if there exists a non-deterministic Turing machine that computes it up in time t sub m of n. What do I mean by non-deterministic? I mean this transition function, instead of going here, goes into the power set of here. If I replace this right-hand side with its power set, you essentially get indeterminism in the context of computer science. It's not random, but it is non-deterministic. You don't know what single output to yield. So all functions that you could solve in polynomial time on a non-deterministic machine, you call that NP. So the P versus NP conjecture asks the following. We know that P is contained in NP, but we do not know about the other way. We do not know if this is a strict inclusion, and we do not know if whether this is an equality or not. So essentially, as computer scientists and some logicians would insist, the next step from Gödel's incompleteness theorem would be the P versus NP problem. Once we've dealt with computability, but we have still not dealt with complexity or efficiency.
You can have very different algorithms. Some will take a very long time, some will do it fast.
Right? In fact,
Any examples of NP algorithms? Any examples?
trying to emulate a quantum computer on a classical computer. That's NP. You don't have a polynomial time solver for a quantum computer simulation. Then there's a bunch of other problems as well. The traveling salesman problem is NP complete. So not only is it NP, it is generalizable to an arbitrary NP problem.
So if P is equal to NP, then the traveling salesman problem and the quantum being simulated on the classical computer, that can be achieved in polynomial time. We just haven't found the right algorithm yet.
Right.
That's what it means.
That's what it
P
implies.
is equal to NP.
Though I will have to take a rain check on the quantum simulation statement I've made, because one caveat I forgot to mention is that we still do not know the relation between quantum time complexities and NP. We don't know. We don't even know if they intersect as of yet. Well, they intersect on P, but we don't know if they intersect beyond P because of probability.
Overall question.
Go ahead.
Yes. Anyhow, you made Turing machine, Haashir. Could you think there will come a future when machines made by us will overtake us, or we will keep them under hand?
That seems to be a combination of artificial intelligence and whatnot.
That time
Okay, truth be told, I would be in the camp that does not believe so because of the fact that any machines we build or any artificial intelligences we build, they're still governed by mathematics and physics for the most part. As long as we're in charge of those, we should be good.
We would keep on excelling.
Pretty much.
Okay, good.
Okay, good. Thank you.